welcome to Target IAS. I am Om Prakash Rajput, and today we will see applications of Gauss law. So yesterday we have in the previous video, we have learned about the Gauss law. What was that? It was the total electric flux. The total electric flux will be total electric flux through a surface will be equals to the total charge enclosed inside the surface we are considering, and the total electric flux is given by d dot ds. The dot product of d and d is displacement flux density and ds vector the surface we are taking, and it is an closed surface, and the charge which is present inside that closed surface will give the total electric flux. This is Gauss law, and we have seen its differential form also. Del dot d is equals to rho v if the charge is present over a volume. So this equation will be there. Del dot d is equals to rho v. This is the Maxwell's first equation also. So using this Gauss law, we will see some applications of Gauss law. That is, the displacement flux density we will find out due to point charge, line charge, and surface charge, and the volume charge also. So before that, for a for Gauss law to be applied, we need a surface which is called Gaussian surface. So a Gaussian surface should have some properties, that what Gaussian surface should be taken. Gaussian surface is taken such that the d at Gaussian surface, whatever surface you are taking as Gaussian surface, d at Gaussian surface should have either tangential component or normal component. Either it should have tangential component और it should have normal component. अब इससे होगा क्या, क्योंकि d डॉट ds डॉट प्रोडक्ट है यहाँ पर, तो ये d ds cos थीटा हो जाएगा. तो अगर टेंजेंशियल कंपोनेंट होगा, इफ इट इज अ टेंजेंशियल कंपोनेंट, तो ds वेक्टर क्या हो जाएगा, उसके परपेंडिकुलर हो जाएगा, यानी कि वहां पर थीटा 90 डिग्री हो जाएगा फॉर टेंजेंशियल कंपोनेंट. तो डी डी एस कितना हो जाएगा भाई, मतलब डी डी एस कॉस थीटा कितना हो जाएगा, 0 हो जाएगा. ठीक है. इफ इट इज नॉर्मल कंपोनेंट, तो क्या होगा, जैसे ये सरफेस है, ये इसका डी एस वेक्टर है, और डी भी नॉर्मल ही है, सरफेस के नॉर्मल ही है डी एस, डी भी. ठीक है. डी और डी एस वेक्टर दोनों के दोनों नॉर्मल है सरफेस के, तो इनके बीच में एंगल क्या हो गया, थीटा इक्वल्स टू 0 डिग्री. तो इस केस में जो d डॉट डी एस है वो क्या हो जाएगा, इट विल बी somewhat, cos theta 0 cos 0 will become 1 and just d ds will be remaining. ठीक है. तो इस तरीके से आपको गॉसियन सरफेस लेना है, दैट इट शुड हैव ईदर टेंजेंशियल कंपोनेंट और नॉर्मल कंपोनेंट. The other property is that you can take whatever shape you want to take. You can take whatever shape you want to take, but it should be such that it should enclose the whole charge which you are considering. It should enclose the whole charge. It can be of any shape, it can be of irregular any shape. It should enclose the whole charge, and for enclosing it should be a closed surface. It should be a closed surface. It should be a closed surface, क्योंकि गॉस लॉ सिर्फ और सिर्फ क्लोज सरफेस के लिए ही एप्लीकेबल है. मैंने एक प्रीवियस वीडियो में भी बताया था कि गॉस लॉ जो है वो क्लोज सरफेस के लिए ही वैलिड है. next thing you should take care of that the surface you are considering as Gauss surface, it on the surface the normal component normal component of D should be should be constant all over the surface, all over the surface is it should be constant। as इस तरीके से आपको मतलब गॉसियन सरफेस लेना है कि जो नॉर्मल कंपोनेंट आएगा जो सरफेस आप कंसीडर कर रहे हो उस पर वो कांस्टेंट रहना चाहिए, वो कांस्टेंट रहना चाहिए, इट इज कांस्टेंट। सो ये कुछ प्रॉपर्टीज थी गॉसियन सरफेस, ताकि इजीली आप क्या गॉसियन सरफेस आपको कंसीडर करना चाहिए वो समझ में आए। So the first application we will see is electric flux density due to a point charge. Electric flux density due to a point charge. So let us first consider a point charge. Here is my point charge. Now through this point charge the flux line will go, as this is a positive charge which I am considering, the flux line will go radially outwards, and I have to consider a Gaussian surface to apply a Gauss law. So what I can take as a Gaussian surface will be a sphere, because first I make then I will tell। अब यहाँ से flux lines will be radially outwards to it, and you can see that at every point on the surface, at every point the flux lines are normal, because यहाँ पर आप देखोगे तो ये इस डायरेक्शन में, तो ये इस सरफेस के नॉर्मल है, यहाँ पर आप देखोगे तो ये इस सरफेस के नॉर्मल है, यहाँ पर ये 90 डिग्री का एंगल बनाएगा। तो you can see that they are normal to the surface, and you can also see you will know that on the surface the D will come same, and it is having only normal component of the flux D vector. Now we apply the Gauss law. Suppose this Gaussian surface has a radius of r, because that is also required, because we want to know the surface area for this, and this is a sphere basically, ठीक है, which I have taken a Gaussian surface। जो इस प्रॉब्लम के लिए कंसिडर किया गया गॉसियन सरफेस वो एक स्फीयर है। तो यहाँ पर गॉस लॉ अप्लाई करते हैं। व्हाट द गॉस लॉ सेज इज दैट क्लोज इंटीग्रल ऑफ is d.ds is the total charge enclosed in it। तो suppose the charge is enclosed here, the point charge is of the value q, point charge is of the value q, so d.ds, and the ds vector will be here in spherical coordinate, it will be in the direction of ar cap, it will be in the direction of ar cap। So d.ds will become here, if you will apply, it will come as d ds, the surface area of sphere is 4 pi r square, 4 pi r square, and the total charge enclosed is q, so I can write d as q by 4 pi r square। This thing we have already uh, written, this thing we have already know that when we were writing the definition for electric flux density, what was it? The total charge, the total flux over passing through an area, total flux passing through an area, there were no closed surface, so here the Gauss law here we are applying, this is a closed surface, so d किसी भी सरफेस के लिए निकाला जा सकता है, बट गॉस लॉ के लिए हमको क्लोज सरफेस ही चाहिए, ठीक है। लेकिन हम पॉइंट चार्ज के लिए इलेक्ट्रिक फ्लक्स डेंसिटी की वैल्यू निकाल चुके हैं इस तरीके से, ठीक है। अब ये गॉस लॉ से यहाँ से प्रूव भी हो जाती है कि, या फिर गॉस लॉ प्रूव हो जाती है इस तरीके से, ठीक है। d is equals to q by 4 pi r square, if I write in vector form, so it will have only r component, and also you can write the expression for electric field intensity, because D is nothing but epsilon naught E. D is nothing but epsilon naught E, or if there is a different medium, so it can be epsilon E AR cap. And you know that due to a point charge, the electric field is given by 1 by 4 pi epsilon naught Q by R square AR cap. So here this we already know. Now here we can see through Gauss law we attain the same result here. So this is the first application. Now this is a simple thing which we have done for a using Gauss law for a finding the electric flux density due to a point charge and electric field intensity also. Now let us see for an infinite line charge if we apply the Gauss law. So here is my infinite line charge having line charge density, suppose rho L, and we know for this electric field intensity at a point, electric field intensity at a point, suppose here I'm considering a point, electric field intensity is given by rho L by 2 pi epsilon naught rho a rho cap. You already know this. So let us see if we can find the same result using Gauss law also. Now to apply Gauss law we will require the Gaussian surface. So for this line charge, uh, what Gaussian surface we can take? We cannot take sphere here. We have to take Gaussian surface such that it will have either tangential component or normal component, and every point on the surface which we are taking, the d value should be constant. So what the Gaussian surface here will be? So here I can use this as Gaussian surface. I can use this as Gaussian surface because it is a cylindrical body. We can take cylinder as our Gaussian surface, because you can see that the electric field intensity I am finding at this point, electric field intensity I am finding at this point P. If I find electric field at this point, it will be same as this point P only, and I can find electric field intensity at this point, it will be also same electric field intensity, or you can say electric flux density. There is only a difference of epsilon naught, so which is a constant, so both can be applicable. That for a Gaussian surface, either you can say that electric flux density should be constant or electric field intensity should be constant. For all these points I am taking on the curved surface of the cylinder is constant. Now we will see here if we apply Gauss law, what it will be. Again, the closed surface integral d dot ds should be equals to the charge enclosed in it. As this is a line charge, so I can write it as rho l dl, rho l dl. So d dot ds, now there are three surfaces in this cylinder. One the top part here, this one, and one is here the bottom part, and one is this curved surface. So I have to take the surface integral of all the ones. Suppose this is my first surface, this is my second surface, and this curved surface is my third surface. So I have to do first surface integral plus second surface integral plus third surface integral. So here d is everywhere, d dot ds, d dot ds, d dot ds here. This will be equals to the integration of rho l dl. So let us see the for the first surface what will happen. The electric field intensity direction or the displacement flux density direction, where it will be. For the first surface, the electric field intensity due to line charge will be in the rho direction only, in the rho direction only. For bottom surface also, the electric field intensity or the electric flux density is in the rho direction only, in the rho direction only. So the top and the bottom surface will have only tangential component. Tangential component. What is the surface vector for the top part? What is the surface vector for the top part? It will be like this. It will be like this. Now you can see this is the direction of D and this is the direction of surface vector. So what are they making? A 90-degree angle. So here the dot product of both these will become 0. So the first integral or the third integral, I mean the first surface integral or the third surface, I have taken it as second. So second surface integral will become 0, as this surface has a ds vector in downward direction, but the displacement flux density direction is here, so it is also making a 90-degree angle here. So both these becomes 0. The only thing remains is this. So we have to evaluate this integral only, the third part. So I can write like this: integral d dot ds over this curved surface equals to the charge enclosed, which will be rho l into L. So what this become? D ds. What will be ds? What is the curved surface area of cylinder? It will be 2 pi rho h. If I consider the Gaussian surface height of h, here for height h, the charge will be rho l into h. Here this h on both the sides gets cancelled. What you get as d is rho l by 2 pi rho. If I write in vector form, it will be aero cap. You know that on the curved surface the direction of the d will be in aero cap direction only. Here it will be in the aero cap direction only, right? So you can write in the form of vector also. This form you have seen earlier too for a line charge: rho l by 2 pi rho, rho l by 2 pi rho d vector. We have already seen it. Now we can also write from this equation only epsilon naught e, if I am considering free space, 2 pi rho aero cap, and e can be written as rho l by 2 pi epsilon naught rho aero cap. This equation we have already derived in the derivation of electric field intensity due to infinite line charge. So here also we have seen using Gauss law we can arrive at this equation. So this is the electric field intensity, or this is the electric flux density due to a infinite line charge, and we can find these things using Gauss law also. So these this is some applications of Gauss law. Now we can use Gauss law for a surface, I mean for a surface charge density also, just as like we have used for line charge and a point charge. So what we have to consider is a surface charge, and then we have to see then we have to find a Gaussian surface for it, and on that we can find the displacement flux density and electric flux density, and we can uh, think of uh, what we have found earlier. So let us consider a surface charge here. Now here is my infinite sheet charge having rho s surface charge density. For this I have considered this Gaussian surface having an element ds here. Now you know that for a surface charge density the electric field direction will be first in the normal to the surface in the upward direction. Suppose this is if I take the coordinate system. This is x, this is y, this is z. So this is in az cap, and the downward direction minus az cap. This will be the direction of electric flux density or electric field intensity for the surface charge. Now I have considered this Gaussian surface which is cutting the surface like this, and I want to check that what is the if I apply the Gauss law, what will be the result. So here you can see that it is having six surfaces. It is having six surfaces, and as per the requirement, I have considered this as a cuboid type Gaussian surface. So here, if we apply the Gauss law, we have to apply the Gauss law for the all the six surfaces to so that the uh, closed surface can be called. So what is Gauss law? It is d dot ds equals to the charge enclosed. As this is a surface charge, so I can write as rho s ds. I can write it as rho s ds. Now the charge enclosed here will be what it will be, this area multiplied with the surface charge density, right? Now we'll see the surface vector of the surfaces of the Gaussian surface. So surface vector for the top surface will be in this direction, bottom surface will be in this direction, and for sides it will be like this. So you can see for the four sides, this side, back side, and this left side, for sides the surface vector and the displacement flux density vector or the electric field intensity vector are perpendicular. So I can write it as for d dot ds for sides plus d dot ds for the top surface plus d dot ds for the bottom surface. Now this value will become 0 because d and ds, here d is in the az direction, and the surfaces the ds vector for the sides of this cuboid will be in either the x direction or in the y direction, which means they are perpendicular, and dot product for perpendicular vectors is 0. So this integral will be gone, only the remaining integral will be this. Now let us evaluate this, what it will be. So here if we evaluate this, so what will be the ds vector for upper part? It will be if I am considering the coordinate axis as xyz, so it will be d, and ds vector will be dx dy, and for the top surface it is az cap. For the top surface it will be az cap, and here d vector for the top surface is also az cap, so a dot az cap dot az will become 1 plus here this d dot ds. Here for this bottom surface, what will be ds? So it will be also for the bottom surface in the same direction, they are in same direction, so it will be something also like this d dx dy, right? So it can be written as 2 integral 2d, I mean dx dy, which is equals to the charge enclosed, which is equals to the charge enclosed in it. तो charge enclosed कितना हो जाएगा इस पूरे एरिया में? It can be written as rho s integral, because rho s is uniformly distributed charge, here I am considering, so rho s can come out of the integration, and ds can be written as dx dy. And what will be the unit vector if I consider here? So I will write the unit vector later, because we know that for the upper part it will be going az cap, and for the bottom part it will be going minus az cap. So here this we can equate now these two. because here also integral of dx dy, here also integral of dx dy. So whatever the surface, we can write it as 2d is equals to rho s and d is equals to rho s by 2. And if I write in vector form, it can be written as like this. So this equation also we have written earlier, and if I make it in the electric field intensity form, so it can be written like this: E vector is equals to rho s by 2 epsilon due to infinite surface. You know this. So here also we get the same equation using Gauss law for an infinite surface charge. So we can apply Gauss law on anything and consider a Gaussian surface, and you can get the electric flux density and electric field intensity. So here what we have seen in the application of Gauss law, whatever we have considered earlier as point charge, line charge, surface charge, and we found the same equation for them using Gauss law too, as we have found using Coulomb's law, we can say using Coulomb's law here. So we can say that we have proved Gauss law using Coulomb's law here. Now let us see another topic on application of Gauss law: electric field intensity due to conducting sphere. Now for a conducting sphere, it is not a hollow sphere, it is a conducting sphere. For a conducting sphere, whatever the charge in the for this conducting sphere, it will be spread uniformly over the surface. For a conducting sphere, the charge gets uniformly spread over the surface. There will be no charge inside the surface for a conducting sphere. There will be no charge inside the conducting sphere. All the charge will be spread over the surface uniformly. So now we want to find electric field intensity due to this sphere at every point. At every point by mean that outside this sphere, inside this sphere, and on this sphere. So what I have to do is use Gauss law to find this, because that will be easier using Gauss law to find the electric field intensity at every point. So suppose for this point I'm saying, and I'm considering this sphere as radius r, let us say, or we can let us say r, and I'm finding electric field for 0 to not 0 to infinite. So this is my radius of the Gaussian surface. So it will have three cases. It will have three cases. So let us say the case 1, where the r is varying from the capital R to infinite. Capital R to infinite. Which means that the point of point at which we are finding electric field intensity is outside the conducting sphere. So what I have to do is I have to consider a Gaussian surface for this. I have to consider a Gaussian surface. So let us say I have considered this sphere as my Gaussian surface, which is having radius small r. Now using Gauss law, what you can say is that d dot ds is equal to the total charge enclosed in it. The total charge enclosed in it. So let us say the charge on this sphere is q. The charge on this sphere is q. So what will happen now? D dot ds it will have a direction radially outward, and the surface vector will also be radially outward. Ar cap, which it means, because it is a sphere, so let us say spherical coordinate system. So d vector and ar cap are in the same direction, so the dot product becomes d dot ds. This will become, d will come out, and we will see what will be the ds, and the total charge enclosed is q. So here d into the surface area for this sphere will become 4 pi r square equals to q. You can find this surface area also. If I write in place of ds, if I write in place of ds r square sine theta d theta d phi, because this is nothing but a sphere. So for sphere, in the direction, if the direction of the vector is in the direction of ar cap for a surface, so what is the differential surface for that? It is r square sine theta d phi, where the limits of theta are from 0 to pi, and for phi they are from 0 to 2 pi. So you can also solve this. If I integrate this, so r square will come out, and what is remaining? Sine theta d theta, as they are independent, so I can write them in independent integrals. So here this will become r square sine theta integration will be minus cos theta, and here pi it will be, so limits are from 0 to 2 pi, cos minus cos theta limits are 0 to pi, and if you solve this, r square cos pi will become minus 1, which makes it plus 1, and minus uh, uh, what is this? Cos pi here is, and minus the lower limit, minus minus becomes plus, so here it becomes 1 plus 1, and here it becomes 2 pi. So you can see here also we are getting 4 pi r square. So this is the surface area for sphere, so which I am writing here. So now what the d becomes? D becomes q by 4 pi r square. I can also write E is equals to q by 4 pi epsilon naught r square, and if I write in the vector form, it will be E equals to 1 by 4 pi epsilon naught q by r square ar cap. So this is if the point of interest, or the point at which I'm calculating the field, is outside the conducting sphere. So it will behave like a point charge, because we are getting the same formula for for a point which is lying outside this sphere. It will be like a point charge, but it's actually not. So now this is the condition for this case. If the Gaussian surface radius is from the surface to the infinite, it is having radius from, which is r, capital R, to infinite. Now let us consider the second case, which is at the boundary. That means for case 2, r is equal to r, which means that the Gaussian surface which I will take, which will be on this surface only, on this surface only. The Gaussian surface which I will take will be on this surface only. So it will be something like this. So this is my new Gaussian surface for case 2, where r becomes capital R, small r becomes capital R. So what the we will apply the Gauss law. D dot ds equals to the charge enclosed, equal to the charge enclosed. here also the charge will be q. Here also the charge will be q, and d dot ds having same component because the surface vector and the d vector are in the same direction, that is ar cap. So this becomes again d into 4 pi. Now as r is the small r is equals to capital R, so I can write here as this 4 pi capital R square equals to q, and I can write as d is equals to q by 4 pi r square, and E is equals to q by 4 pi epsilon naught r square. And if I write in vector form, here, it will be q by 4 pi epsilon naught r square, right? This is when the Gaussian surface which I am considering is on the surface of the conducting sphere. Now the third case, this is a case 2. The third case is when r is less than this radius of conducting sphere. So this was my conducting sphere, and now I'm considering the Gaussian surface inside this, which means that my field point is like this on this surface somewhere. So now if I apply again the Gauss law, d dot ds equals to, now what is the charge enclosed? I have told that for a conducting sphere all the charge will be on the surface of it. All the charge will be on the surface of it. There will be no charge present inside the conducting sphere. So as there is no charge, what is the charge enclosed? What is the charge enclosed in it? It will be 0. So we can say here d becomes 0, E becomes 0, right? So this is the condition for this case. Now we have found 3 conditions basically. We can also plot this if we want to plot this on a graph. So we can also plot this, wait, so we can plot this also. So here if I consider, here is my electric field. If I write, here is my electric field magnitude, and here is the radius of the Gaussian surface which I am taking. So based on this, up to r, up to r, up to r means the capital R, when the r, small r, becomes the capital R, up to that value the electric field is 0. I mean when r is just less than this capital R. At this, in case 2, what we have found, the electric field, it is this q by 4 pi epsilon naught capital R square. So suppose this is somewhat here. If I made this as a straight line, if I write R here, so it is here. This is R, and at this point the value of the field is q by 4 pi epsilon naught capital R square. After that what is happening? After that what is happening? You can see that here 1 by 4 pi epsilon naught is constant, the charge q is constant. You can see that E is varying inversely to the square of the distance. E is varying inversely to the square of the distance. So what you will get? You will get a graph something like this for E inversely proportional to R square. So this is the value of electric field graph when the Gaussian surface which I'm taking, depending on that. So up to the capital value of r there is no charge, so electric field is 0, and at the surface it is maximum, and after that it is decreasing inversely to the square of the distance at which I am considering the Gaussian surface. So these are some applications of Gauss law. We will see more use of Gauss law. We will apply a Gauss law on different things now, but in the next lecture. So this is all for this video. We'll meet in the next lecture. Thank you.